continue week 13A, frequency response. Now, this is part E. We'll be finer part and speed up some explanation, and then we'll point out at important things that you need to remember and something that you'll be able to do, especially for the exam. So for second order body plot, let's start with the low frequency. Second order, there are two. Um, s to s square plus 2 xi omega n s plus omega n square. N is natural frequency or resonant frequency. You can express in many ways. We talked about that in class. So we will be expressing, this is something you saw often in forms of 1 over in denominator. For this one, let's say, just say polynomial, second order, and in a numerator. Let's rearrange it in terms of omega n squared, because you can pull it out and it's a number. These are depending these. So s squared over omega n squared plus 2 xi s over omega n, because you're dividing by omega n squared, and there was 2 xi omega n s, so those cancels out, so you're purely left with s over omega n. I'll clean up it. And since you pulled out omega n squared, it's omega n squared over omega n squared, that is 1. So you have in terms of this. Does it look familiar? Maybe not yet. So let's just deal with the low frequency first. At low frequency, so from the generalized form, at low frequency, omega n squared is omega n squared, the magnitude, and phase is 0. So 20 log m is 20 log g of j omega, where you place s equal j omega. You end up with, since you only have the magnitude n omega, you end up getting this value. So continuing on, what would if it is at high frequency? At high frequency, when omega n is high, that's 0. That's very insignificant. Omega n squared cancels out, so you end up with s squared. And since you're replacing s with j omega, and you have something like j omega squared, that is j squared omega squared. J squared is minus 1 omega squared, so that is minus omega squared here. And absolute value of it is omega squared, and you have minus omega, and that is 180 degree. So phase is 180, and you have omega n squared. Now you can express as a 20 log m, 20 log of g of j omega. That was happened to be omega squared. 20 log omega squared is the same as 20 log omega plus 20 log omega, which is 40 log omega. Or you could have put this one here as a 2 times a 20 log omega. Same thing. So let's start with the body asymptote with normalized and scaled. Normalized and scaled, you notice that the omega over omega n, and the 20 log m omega n squared. So that is your magnitude in dB, and this is your frequency in scale. It's not like a 1 hertz, 2 hertz, or 3 hertz, or 1 rep per second, 2 reps per second, but it's normalized to the frequency of your interest. So at that place, instead of a 20 dB per decade, for the second order system, it's increasing. Do you notice? Per decade, that's a 40 dB per decade going up from the frequency of interest. Similarly, so before it was 20 dB for the first order, so S plus omega type thing, or S plus A type. Now it's omega squared. Next one is phase angle in degrees. We'll just write down minus 90, minus 45, 0, 45, 90, add another 45 degree, and etc. So point of interest at 1, it crosses, instead of 45, it crosses 90, and it's starts at 0, crosses 90, and starts at 0, crosses 90, all the way to 100 at 10 times that, and it flats out. But how do you really plot the second order body plot? Because those are asymptotes, it's not real. I mean, it's not the exact value, not real and imaginary, but not in being exact value. So let's make some correction to it. So starting with a g of j omega, g of s, it's s squared 2 xi omega n s, and omega n squared. You replace everywhere you see s with a j omega. So now you have j omega squared plus 2 xi j omega omega n times j omega plus j omega squared. You have j omega squared, j omega squared. You have omega n. Let's start working on it. So what am I missing? You have to be careful that this is correct. This is correct. It was just omega n squared, not j omega squared. So I'll just write down omega n squared. So when you're copying it down, you also have to be very careful, especially when you're writing test. So j omega squared is j squared omega squared. Let's move this out of the way, but plus omega n squared plus, here this j comes out, and it's 2 xi omega n omega. So your frequency sweep and your frequency of interest. So let's look at this portion. It's omega n squared. J squared is minus 1. So minus 1 omega squared. So you can kind of rearrange, and that's a fun part. J to zeta omega n omega. So this will be real portion, and this will be imaginary portion. So magnitude, so this is your new A plus JP. So M, the magnitude is A squared plus B squared square root. So your A portion is here squared, and here's your B portion, 2z omega n omega squared, and square root of the whole thing. So that's where this equation came from. And there it's no longer, if you calculate it, 3 dB, and with 5.71 degree for phase angle shift. Now it depends more on, not like a, okay, here's asymptote, and then we'll draw a nice graph like this with about minus 3 dB down. But now it is second order, so it's just something coming, but it will be steeper. Instead of minus 20 dB per decade, it will be minus 40 dB per decade. But what you also need to notice is this portion, and I can emphasize your magnitude depend on value of z. Value of z. What is value of z? Z is your damping ratio. So second order equations and the body plot for it depends on this zeta value. So now again we have normalized and scaled. So it's at one frequency that's been normalized. So what are we interested in? So s squared 2 xi omega n. We do have something depends on, this is coming from a table, but depends on value of xi, and you'll end up getting all these. And remember the magnitude was omega n square minus omega n. That was a real portion. That total squared minus 2 xi omega n squared and square root of it. So you literally find out what, and then 20 log of that, and then you literally find out what will be the dip. So we start with 1, that damping ratio is 0.5. That literally cross 0. There's a slightly small dip under, but that, as the damping ratio increases, your value, it looks smoothly going. So because it's looking like this, the dip is more on the side, but it will be more intuitive when you're working with something like this and then this, or something like peaking and kind of damping. So these peak portion, and upside down, it will look like this. When damping is very, very, very small, and you don't even feel it, it's very close to 0, and then you'll have a sharp pointing portion in your graph. So you calculate each for 1.7, 0.5, 0.3, 0.2, 0.1, maybe 1.5, and find out where it's crossing. 0 for this one, but I'll find out where it's crossing. Same for the normalized scale, the log of phase response, depending on not omega, omega is here, omega over omega n. It all crosses somewhere here, about 90 degree, and its damping ratio is very little, so almost like a no viscosity. There's a sharp change. This one I'm gonna draw in a nice big line, because when there are so many lines it's hard to see. This yellow line I just put in at that frequency of your interest, it's 90 degree, but it's plus 90, that goes to 180, and 0. So what you need to get, I may not ask you to draw this, but what happens at damping ratio is about 0.5 more, so you should be able to pick and see if the damping ratio is close to 0, close to this axis, the frequency axis, and how it is when it's far out. So depends on drawing the phase shift, whether it is more abrupt, like really fast, like a just general shape wise, or very like a relaxed, closer to asymptote, and that's depending on the value of zeta. Higher, closer to the asymptote, lower, closer to this vertical. So I just explained, but it wasn't recorded, so I'm gonna quickly say it. 1 over s squared plus 2 xi omega n s plus omega n squared. Now it's in the denominator. You just need to pay attention to it peaks. When zeta is closer to 0, it's kind of rounded. And when zeta is larger than 1 and larger in general. Same thing with the normalized and scalar low magnitude. Instead of going up, or instead of S shape, for when it is in numerator, and now it's in denominator, so it looks more like going down. This was more so going up, and still crosses over it. I'm not crossing here, PartE, literally. When it crosses over minus 90, it will be more on this shape. So I want you to work on your example 10.3. This has all the answers in there as well. So first thing you will find out is, oh, you have a 0 and 3. I'll get minus 3, literally. So 1, 2, 3. Let's see. And then 0. Okay, that is 20 dB per decade. On your denominator, we have s plus 2, so something will be going down at 2. And then do you notice this one's going down? So actual graphs will be coming along, and that is this red I can erase. It's just to show, okay, that is 3, this point is 2, this point is 3. What's going on with this? So you do have to recalculation. S plus 2s plus, what will be good? 2 squared, 4, that would mean s plus 2 squared, right? Because it's 25 minus 4. So you do manipulate that, you'll end up getting 1 over s squared plus 2s plus 25. You divide everything by 25, 25, 25. And then, of course, you have to get 25, 1 over 25 to the front. So that is each one at 1 over 25. And then 1 over 2, 1 over 3, 25 times 2, that is 50, and then 3. It's all the gathering of coefficients. And log, 20 log that is approximately this value here. Okay, it looked a bit messy, but this portion, that's why you have to draw whether it's S or 2 or 5. Can you tell? So these are 25 over 25, and this was 2 times 25, and this was S over 25. So you place in forms, you're not solving the quadratic equation just like in the early attempt, but literally placing everything in square. That will be 2 xi omega, and that will be omega square, and etc. So when you complete that, you will end up with some graph. The key is being able to individually draw each line that speaks of each one of these, including what will come out. But then the second step is more critical. You identify everything in there, and then you start working. Also, somewhere between minus 20, 30, that's where we are starting. I'm going to follow with a yellow marker. There wasn't, nothing was bugging it until at 2. So at 2, something happens. Let's see, at 2, oh, it's minus 20 dB per decade. So you have minus 20 per decade per slope. But right at 3, we have 0. That's interesting. We had a pole going down 20 dB, and also we have 0. So it will be minus plus, it will be flattened. So let's keep going until it meets this 1, 2, 3, 4, 5. So 5, that's nice, but it's in 0. So 헬도 가면 되니까. So almost going autopilot, and you express that on top of it. So it was flat, and all of a sudden you have 40 dB before 1, 20 dB up, 20 dB down, 40 dB down. So it was flattened from that point of your interest. 1, 2, 3, 4, 5, and s equal 5 minus 40 dB. So you draw this here in the blue. Now my marking. You drew the asymptote first, and then you calculate its damping ratio, and what depends on the damping ratio. I'll figure out the zeta and calculate it, and we'll see okay, it's up to here, but bit of a bump. It may not come out looking nice. If it wasn't nice straight, it would be just peeking right at it. But let's look at this. 1, 2, 3, 4, 5. So 5 is still the largest or biggest or peak, and then it will kind of smooth and take the shape. So the fact that S squared taking shape in the mix of first degree, first order, and second order, it will be interesting to see whether you can smooth it out. So for skill assessment, this is relatively simple. This doesn't have any second order separate second order one yet. So it's all first order that's been put together. And point of interest, find the point of interest will be s equal minus 1, s equal minus 7, s equal minus 50, s equal minus 20. I would say they're all the precious ones that you need to take care of. Anything in the denominator will be going downhill. Anything in numerator will going uphill, both by 20 dB per decade. And then you'll be able to figure out and draw this on a Bode plot in the log, semi-log scale graph I gave you. So there are more skill assessment, and the example of a stability gain phase margin via Bode plot, and we'll continue in next time. It is pretty much in chapter 10 of EECE as acknowledgement. Thank you. That concludes week 13A.